Hello friends. So in the last lecture, we actually started with film condensation, and we looked at the mathematical formulation for film condensation using boundary layer approximation, considering the falling film from the vertical flat plate as a very thin film, and applied the boundary layer equations to the liquid film, and were able to derive an expression for laminar film condensation, the thickness of the layer delta, and from that we were able to get the expressions for the heat flux or the total heat transfer rate per unit width of the plate of length L, and the total condensation rate at length L from this one, from the expression that we had derived. Right? We had derived an expression for NuL using what we call as the Nusselt analysis. So what is special about the Nusselt analysis? Let us just try to recall that. So in the Nusselt analysis, the primary distinguishing feature is the assumption of linear temperature profile inside the liquid film. So it assumed that from the wall to the edge of the liquid layer, where the wall temperature is T wall and edge of the liquid layer would be at the saturation temperature because it is in contact with the vapor. And Nusselt assumed a linear temperature profile 1 minus y by delta for Tsat minus T by Tsat minus T wall. And with that, the expression that was derived had a HFG prime, which was defined as CPL times Tsat minus T wall divided by HFG, right? So, sorry, CP 3 by 8 times CPL times T wall, Tsat minus T wall subtracted from HFG. So that was the expression for HFG prime. This is the expression for HFG prime that we had derived. Later, we said that Rosenau, when he did the analysis, he said that why do we need to assume a linear temperature profile? We can do the integral analysis assuming a more complex temperature profile. So he assumed a power law temperature profile. I think it's a third degree power law temperature profile, just as we do for a Baudelaire temperature profile. And with that, the constant changed. So instead of 3 by 8 that we had in this expression, the 3 by 8 that we had in this expression, which is because of the integral arising from multiplying 1 minus eta and get this profile. So instead of that, if you substitute the cubic profile and integrate, then you get the expression that Rosenau got, where instead of 3 by 8, he got 0.68. Right? So that is the main difference between the simplified analysis of Nusselt and the integral analysis of Rosenau. So then the Jacob number was defined, so which is defined as CPL into Tsat minus T wall divided by HFG prime, and HFG. So you get HFG is equal to HFG prime is equal to HFG times 1 plus 0.68 Jacob number in the Rosenau's expression, whereas it was 1 plus 3 by 8 Jacob number in the case of the Nusselt expression. Okay. Both of these, of course, are valid only for laminar condensation films, and the expression that we write for the global energy and mass balance, that is the total heat transfer from the wall, from the vapor to the wall per unit width of the plate of length L, is given by QL prime dot, and that is equal to HL bar multiplied by Tsat minus T wall, which is the heat flux multiplied by the average heat flux multiplied by the area, which is L into 1. And since HL by KL, H bar L by KL is Nusselt number, this can be rewritten as KL times T sat minus T1 into NUL bar. So this is the expression, and NUL bar is given by the expression that was derived by Nusselt, except that the HFG prime expression can be replaced now with this one. So that gives you the QL bar and the QL dash, and ML prime, which is the mass flow rate of condensate that is going to be collected over the plate over unit width of the plate of length L, and that from the overall mass by energy balance, m dot L prime multiplied by HFG prime should be equal to QL prime, and therefore this ML prime is equal to Q dot L prime divided by HFG prime, and that gives you this expression. Okay. So we said that if the NUL bar were valid for wavy as well as the turbulent boundary layers, then these expressions are actually valid for all kinds of film condensation, because there is no assumption made in writing these expressions. Only the NUL bar has been derived using the laminar assumption here. So if I use this expression for laminar film, then I would get these for the laminar case. Now we'll also look at how we get the NUL bar for the turbulent case. But before that, let us also drop a couple of more assumptions that we had made in the previous class. So what are the assumptions that we had made in the previous class? One assumption that we made, of course, was the Nusselt assumption, which is the straight line temperature profile, which we have already removed. But the other assumptions that we made were in the beginning of the last class. So let's just go back to those assumptions. So we assumed that there is no vapor flow, right? And therefore there is no shear on the liquid film from the vapor. So this is one of the assumptions that we had made. And the second assumption that we made was to neglect the inertial term and write only the so this is one assumption, and this is the second assumption. The first assumption is that there is no vapor flow, and therefore there is no shear from the vapor on the liquid film. And the second one is the neglect of the inertia term. So there are works in the literature where these assumptions were also relaxed. So we'll talk about those first, and the scale analysis done by Bejan, so that we get a more general expression which removes the approximations that we had made in the current analysis. Okay. So the first one is about Sparrow and Gregg. So Sparrow and Gregg actually did similarity solution. And he did the similarity solution after removing the assumption that negligible inertia. Okay. So the entire boundary layer equations were solved using the similarity method. Okay. So the boundary layer equation that we wrote here were completely solved using the similarity method by Sparrow and Gregg, instead of dropping the left hand side and writing only the right hand side, which we have done in this case. He did not do that. They did not do that. Sparrow and Gregg actually wrote the entire equation and then brought it down to the similarity form and solved the similarity equations. Okay. So with that, what they found is that the Nusselt number is slightly lower than what is predicted by the Nusselt correlation or the Rosenau correlation. Okay. The Nusselt correlation is for linear temperature profile, and the numbers get altered a little bit when we use the cubic temperature profile, where this 3 by 8 is replaced by 0.68 here. Okay, so what Sparrow and Gregg found is that the Nusselt number NUL bar is lower than what was given by the Nusselt correlation for a certain set of cases. What are those cases? NUL bar less than NUL bar, let us call it as the Nusselt correlation, NUL bar NU, for one is Prandtl number less than 0.3, and second is Jacob number greater than 0.01. For these cases, they found that there is a deviation. Then after that, okay, so we will not go into details of these results, but we will show the details of the next set of results. Chen was the other researcher who removed the assumption of zero shear. So what happens? So you have a plate, and there is this film, and there is also a vapor flow that goes alongside it. So there is some shear stress between this vapor flow and the liquid film. What then happens is that this tries to accelerate the liquid film much further and suppresses the flow. That is something which results in some more change. So this also resulted in NUL bar lower even than Sparrow and Gregg results. Okay, so let us try to plot these results and understand how they were different. So if I plot NUL bar divided by NUL bar NU, okay, so this is the actual average Nusselt number divided by the average Nusselt number predicted by the Nusselt correlation. Okay, so suppose this line is 1.0, okay, and let us say there is 0.8, 0.6, 0.4, etc. And on the x-axis, you plot the Jacob number, which is equal to CPL into Tsat minus Twall divided by HFG. Okay. Now, if I plot this, what they found is that for Prandtl number, okay, so let me put values also here. So there is a 0.01, 0.02, then we got 0.1, it's a logarithmic scale, 0.2, and there is a 1, and there is a 2, and so on. So it's a logarithmic scale, that way it's where it goes. Okay, so what is seen here is that for Prandtl number equal to 1, it goes exactly here. For Prandtl numbers greater than 1, it varies slightly upwards. So this is Prandtl number tending to infinity. So this is, let's say, Prandtl number equal to 10. This is Prandtl number equal to 1. Okay, and for Prandtl number less than 1, it starts departing somewhere close to this 0.2 and goes like that. This is Prandtl number is equal to 0.3, and then there is 0.1, then there is 0.03, and then there is 0.01, and then there is 0.02, 0.003 and 0.001, etc. This is Prandtl number. Okay, so this is the kind of result that he obtained. So for values of Jacob number higher than 0.01 and for Prandtl number less than 0.3, there were deviations in Swaro and Gregg results. And what Chen found is that for low Prandtl numbers, the results are substantially different. Okay. Now, Bejan did a scaling analysis. By now, you would have figured that Bejan is pretty good at scaling analysis. So what he actually found is that for Prandtl number of the liquid, this is actually Prandtl number of the liquid. Okay, so for Prandtl number of liquid, if it is greater than the Jacob number, then he found that the liquid film is restrained by friction, and if it is less than Jacob number, it is restrained by inertia. So in the scaling analysis or order of magnitude analysis, he dropped the appropriate terms, and he was able to show that this entire graph of all curves between 0.003 to 0.3, all of these curves could be collapsed into a single curve. So that's basically what he tried to plot here. Here it is NUL bar divided by NUL bar Nusselt. Okay, on the x-axis, instead of the Jacob number, he plotted PRL divided by Jacob number. Okay, so this ratio, and if it is 1, there is a changeover. So suppose this is your line 1.0, okay, and this is your the dividing line between inertia and friction. Then he found that this line goes something like this, where beyond Prandtl number by Jacob greater than 1. So, when Prandtl number is greater than Jacob number, then it is friction dominated. And below is inertia dominated. Okay, so all of these lines could be just restrained into this much, and this actually contains Prandtl number equal to 0.003 to 0.3. All these curves, all of these curves that are shown in this diagram, 0.003 to 0.3, all of these curves could be just collapsed onto a single line like this. And okay, so this is like 0.5 and 0.5 here, and this is approximately 0.85. So this is the way the curve typically goes. Okay, so this you can say all Prandtl number less than 1. So this is basically the curve that he got, and this basically represents all of these Prandtl numbers pretty well. This is what Bejan had shown. Okay. So when we look at the realistic cases, then we calculate the Nusselt number from the Nusselt correlation and get the correction factor from these diagrams, and then multiply it by the NUL bar to get the NUL bar Nusselt to get the correct value of the Nusselt number. So that is the way the laminar Nusselt numbers are corrected for cases where you don't neglect the terms of inertia and the terms of shear stress between the flowing vapor and the liquid film. So all of this is still laminar for film condensation, Now we'll move on to turbulent film condensation. Okay. So in turbulent film condensation, the first thing that we need to know is how do we distinguish, or what is the parameter that tells us where the film would be laminar, where the film would be wavy, and where the film would be turbulent. So Bayesian's analysis of turbulence using the local Reynolds number in the boundary layer. So his scale analysis shows that when the local Reynolds number is greater than the order of 10 to the power of 2, then the flow becomes turbulent, is the analysis that Bayesian shows that practically valid for all kinds of turbulent flows, including the phase change flows. Now, in this case, the local Reynolds number is typically defined as rho L U bar into delta divided by mu L. Okay, where rho L is the liquid density, mu L is the liquid viscosity, delta is the thickness of the film, and U bar is a representative average velocity of the region. Now we know that this rho bar U delta is in some sense represented by the m dot prime of x, right? So we can define the Reynolds number in terms of the mass flow per unit width of the plate. So that is what is typically done here. Rex is defined as 4 times m dot prime x divided by mu L. So this is the definition that is commonly used for defining the Reynolds number of the falling film. If I use this, then for the flow would be laminar, the film would be laminar for Rex less than about 30, and wavy if 30 is less than Rex is less than about 1800, and turbulent if Rex is greater than about 1800. This is commonly the understanding of the non-dimensional parameter Reynolds number, beyond which the flow becomes turbulent in the falling film of condensate. Now, starting from this, now we can actually write the correlation. See, actually, laminar is straightforward because there are no major variations or things of that kind. It's a smoothly falling film, so we can do a good analysis, like an integral analysis we have done. But in wavy and turbulent, because of the kind of variations that happen, it's not easy to do an analytical study and get solutions. So a large number of experiments have been performed by various researchers in various regimes. Okay, some people worked only with the laminar, some people worked with the laminar and wavy region, some people worked with the laminar, wavy and turbulent region, and a large body of data was compiled, and then Chen et al. Compiled the experimental data and derived the correlation. So what is the correlation that they derived? They said that HL bar into divided by KL multiplied by the length scale. They defined something like this: mu L squared by G whole to the power of 1 by 3. So this becomes some kind of a Nusselt number. This is equal to 1.468 multiplied by REL to the power of minus 1 by 3 for the laminar films, which is REL less than about 30. Okay, and this is also equal to, so the same expression, equal to REL to the power of minus 0.44 plus 5.82 into 10 to the power of minus 6 into REL raised to the power of 0.8 PR liquid to the power of minus 1 by 3, sorry, plus 1 by 3, the whole thing raised to the power of half. Okay, for REL greater than about 0.3, sorry, greater than about 30. Okay, so this is the expression that was compiled by Chen et al. Based on the experiments of a large number of people that had done the experiments in various regimes. And the job that Chen did was to look at all of this data comprehensively, compile them and put them together so that this data is derived. And what they found is that this is working within 10 plus or minus 10% accuracy with reference to all experiments that were used in compilation, which is remarkable because the range of data spans quite a large set of experiments, and the accuracy within 10% of all the, so this is the entire for correlation that has been derived is within 10% accuracy with all the experiments. So this is a good correlation, but there is a problem with this correlation. The problem with this correlation is that in most of the cases when we are dealing with film condensation, the unknown that we have is the mass flow rate of the falling film, and this Reynolds number is a function of the mass flow rate of the falling film. So Reynolds number is unknown. So you cannot calculate the Nusselt number in terms of the Reynolds number. We neither know HL bar nor know REL, and so the whole process becomes a trial and error process. So the diagram that represents this one can be shown here. I'll just draw this figure. So here you have HL bar by KL multiplied by mu L squared by G whole to the power of 1 by 3 on the y-axis, and on the x-axis you have REL, which is 4 times m dot prime at L divided by UL, okay, where L is the length of the plate. Okay. Now with this, suppose I write the numbers here. This is 10, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, and 10 to the power of 5. Okay, and here you start with 0.1, 0.2, 0.5, and finally it goes to 1. Okay, so this is how the y-axis is. So this starts at somewhere like 0.7. Okay, and there is a straight line curve which basically is the laminar part of this curve, which is 1.468. Okay, so suppose I call this as equation A and equation B. So then this is equation A, and equation B actually shows a curve that dips down below 0.2 at something like 10 to the power of 4. So it goes like this. This is a more or less a straight line here. It dips like this, and then the values go up, and these way they go up varies with the Prandtl number. So this is Prandtl number of 1 PRL 1, this is 2, this is 4, this is 6, this is 10, and so on. Okay, so somewhere near between 10 to the power of 2 and 10 to the power of 3, the deviations actually start. And this goes. So all of this is given by the equation B. Okay, so this is the curve that you have. So even if you want to graphically do the job, we neither know HL bar nor know REL. So to get the correct point on this graph for a given case is difficult. You only know the Prandtl number. Now that Prandtl number line where your point lies has to be done by trial and error to get the flow rate of thing or REL. So in order to rectify or get over this problem, another method was devised using the same correlations though, but writing the expression in the form of HL bar into HL bar by KL multiplied by mu L squared divided by G whole thing to the power of 1 by 3 is equal to, you write it as REL divided by B, where B is another non-dimensional number, okay, which can be written as B is equal to L, which is the length, into T sat minus T wall multiplied by 4KL divided by mu L into HFG prime. You see that all of these numbers are known numbers, to G by mu L squared whole to the power of 1 by 3. So now B can be easily evaluated. Okay, and for a given value of B, what is the Nusselt number will basically give you the value of R. So the plot is made with B on the y-axis, B, which is actually equal to L times this expression, T sat minus T wall into 4KL divided by mu L HFG prime into G by mu L square whole to the power 1 by 3. So that is the expression for B on the y-axis, and on the x-axis you have REL, okay, which is nothing but 4 by mu L into, okay, you write the REL itself in terms of the mu L squared by G. Wait a second. Okay. 4 by mu L into m dot prime of L. Now this looks like a straight line in this region. So let me just put the values. This is 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5. Okay, and the end of the line is 4 into 10 to the power of 5. And on the x-axis you have 10 here, 10 to the power of 2 here, 10 to the power of 3 here, 10 to the power of 4 here, 10 to the power of 5 here. Okay, and the line goes like nearly a straight line up to 10 to the power of 3, and after that for different values of Prandtl number you have different lines. This is Prandtl number equal to 1, and as you go, Prandtl number 10. Okay, so now what do? You get the value of b from here, and for the corresponding value of b and the corresponding value of Prandtl number, you drop an ordinate and you get the value of REL, and that gives you the expression for the mass flow rate m dot L, and from where you can also determine the QL and so on. So this is the method that is commonly followed for evaluating the turbulent and wavy Nusselt number. So here you cannot use the Nusselt correlation because the Nusselt correlation is valid in a narrow region here, less than 30, but above that, so this straight line would be valid. So basically this graph here, you substitute for this HL by KL into this one from these two expressions, right? So REL by B will be equal to this in the one region and equal to this in the next region. Okay. So that is what is plotted in this form. So if you know B and Prandtl number, then you can get the value of REL. So this is how the Nusselt number for turbulent Prandtl number, turbulent falling film convection can be obtained. Now that is about vertical flat plates. Now if we look at condensation in other configurations, one of the important configurations that we would like to see is a vertical tube and condensation inside it in the presence of vapor flow. That is one correlation that we would like to write, and then write the same expression for condensation inside horizontal tubes when the vapor velocity is high and when the vapor velocity is low. So these are the configurations that we would like to cover before we close the topic on film condensation. Okay, so the next thing that we do is condensation inside vertical tubes, okay, with parallel downward vapor flow. So let us understand what's the configuration that we're looking at. We're looking at a pipe. Okay. So there is vapor flow from above to below, and there is this falling film that is developing here, and there can be wavy and turbulent flow that happens. Okay, and suppose the length of the pipe is L and its diameter is D. The diameter is D. Okay, then we can use the correlation that I'm going to write now for the number HL bar divided by KL multiplied by nu L squared by G raised to the power of 1 by 3 is equal to, this expression looks very similar to Chen's expression, except that it has an additional term, okay, that accounts for the presence of a confinement in the form of a tube and the effect of acceleration and gravity and all that. So this is going to be equal to REL to the power of minus 0.44, which is very similar to what we had in Chen's expression, and plus 5.82 into 10 to the power of minus 6 into REL raised to the power of 0.8 Prandtl liquid raised to the power of 1 by 3. This much is the expression that we already have seen. Now what we are going to write is an additional expression plus, let me write it here, 3.27 into 10 to the power of minus 4 into the Prandtl liquid raised to the power of 1.3 divided by d square, where d is the diameter of the pipe, okay, multiplied by mu L squared by g e raised to the power of 1 by 3, okay, and multiplied by now the viscosity of vapor divided by viscosity of liquid raised to the power of 0.156 multiplied by rho L by rho V, the ratio of densities of liquid and vapor raised to the power of 0.78, and that multiplied by another expression REL raised to the power of 0.4, and there is another term comes RET, I'll tell you what it is, raised to the power of 1.4 divided by bracket 1.25 plus 0.39 multiplied by REL divided by RET, this the whole square, and the whole square bracket which started here, it ends here, raised to the power of half. Okay, so this is the expression that was derived for condensation inside a vertical pipe. So here again REL is 4 times m dot prime L. So this is m dot prime. In this case, it's going to be m dot L itself, because it's a circular pipe and not unit width. So it's m dot L of like a liquid film divided by mu L, and RET is based on the total vapor mass flow rate here. So if m dot V is the total mass flow rate of vapor that is entering, it forms the upper limit of condensation that can ever happen. Okay, so this is defined as 4 times m dot V divided by mu L, that is RET. So REL by RET will basically define m dot L by m dot V, which is the fraction of liquid that has condensed in the process. And this m dot V by pi d. Okay, so this is the basically per unit length calculation. So m dot V by pi d, this m dot L prime, this also stays as m dot L prime, which is m dot L by pi d. Okay, so this, if I remove the prime from here, then it will also be divided by pi d. Okay, so that is the expression where d is the diameter of pipe. So unlike what we did yesterday, which was completely analytical, today we are dealing with mostly correlations of various kinds. Now, in the case where the vapor velocities are very high, okay, then what happens, whether the flow is vertical or horizontal, it does not matter, because the gravity becomes a small quantity and the shear by the vapor becomes the dominant factor. So even if it is a horizontal pipe, for example, with large vapor velocity, where there is an axisymmetric annulus of film that gets set in, and the flow velocity is like this. So the gravity does not affect. So if I look at the cross section, the vapor film will be just about around the periphery, the same thickness. So this happens when vapor velocities are you cannot just loosely say vapor velocities are high, but you need to define a Reynolds number for doing that. So you define a vapor velocity which says rho v into uv, velocity of vapor, multiplied by diameter divided by mu v. This is the vapor velocity. And if this exceeds the 3.5 into 10 to the power of 4, that is 35,000, then we can consider this to be high vapor velocity, in which case I can write the Nusselt number in a simpler fashion, HL bar into D by KL. This is the liquid film Nusselt number for a length L of the pipe. That will be equal to 0.0181 into Prandtl to the power of 0.65 and mu V by mu L raised to the power of 0.078 and rho L by rho V raised to the power of 0.39 multiplied by, so it's basically all the other terms getting dropped off, these terms getting dropped off, and this one getting simplified to this form. Okay, this multiplied by REL raised to the power of 0.2. So when I take the power half from that, RET raised to the power of 0.7. Okay, so it's the square root of what is here, 0.4 to 0.2 and 1.4 to 0.7, and the new denominator also the square disappears, 1.25 plus 0.39 REL by RET. Okay, so this is the expression that you get for high vapor velocities, and for low vapor velocities, what happens in low vapor velocities? Because of gravity, the liquid settles down. So if I look at the cross section of the pipe, there will be a film on this side, but on here there will be a stagnant pool of liquid. So this is more like this. So there is a stagnant pool of liquid. So if you look at the pipe, there will be more liquid stagnating in this region and less in the other region. So that is the effect of the low vapor velocities. The gravity is going to be effective. So this is in horizontal pipes. For high vapor velocities, whether it's horizontal, vertical or inclined, it doesn't matter. It's the same expression because the vapor velocities dominate gravity. So the gravity terms are taken away. But here the gravity terms are important. So in which case HL bar or HD bar rather in this case, D by mu L, sorry, not mu L, it's KL, is equal to 0.555 multiplied by D cube sorry, there is a crash of the zonal, so I'll need to restore the file now. Okay, let me save this. Okay, 0.555 multiplied by D cube into HFG prime into G multiplied by rho L minus rho V divided by KL into nu L into T sap minus T wall, whole thing raised to the power of 1 by 4. So this is the expression for the Nusselt number in horizontal pipes with low vapor velocities, where the liquid film settles down to the lower half of the horizontal pipe and there is a thin film that is coating the upper half of it. So here we will close the topic of film condensation and try to understand dropwise condensation a little bit before we close the topic on condensation. Okay, so now let us so in the lecture yesterday, we actually discussed that when the vapor film condenses, uh, it forms a liquid film which wets the surface completely. So the surface tension coefficients are low, and therefore the wetting angles, the angle of contact are very low acute angles, and therefore the liquid spreads over the surface and wets it completely, and flows along the surface as a continuous film. Whereas what can happen if the surface tension coefficients are high, or the surface is hydrophobic to the liquid in question, then the contact angles become obtuse and the liquid film may not stick to the surface. So wherever the surface has natural faults of some kind, so some cracks or some pits or some imperfections of the surface, that is where the nucleation sites are. So when the plate is cooled, the vapor comes and starts condensing in the small cavities and pits and those things, and then it starts growing into a droplet. Once the droplet grows to a certain size, because it's not wetting the surface but it is just growing with an obtuse angle of contact, either because of the droplet becoming large enough by its own weight and gravity, it flows down, or because of the downward flowing vapor stream, the drag with the vapor stream, the liquid is dragged along. And when this liquid droplet, large droplet, is dragged along, it drags along with it other smaller droplets that are formed on its way and cleans up the surface, and the surface is now clear and exposed to the vapor for fresh condensation. So this results in a larger fraction of the fresh metal surface exposed to the vapor film, as a vapor region, and therefore the condensation rates and the heat transfer rates are much higher. So normally the heat transfer coefficient for the same surface and the same liquid, when the mechanism of condensation is dropwise, can be approximately 10 times larger than the film condensation of the same pair of surface vapor combination. Okay. So this is a very attractive feature, and therefore in engineering people would like to promote dropwise condensation. How do we do this? There are multiple methods by which dropwise condensation is promoted. One is additives to the vapor. So that the additives actually deposit themselves on the metal surface and make the metal surface hydrophobic, and therefore the droplets can could, roll down on it without sticking. So this basically increase interfacial tension with solid surface. The second possibility is to coat the surface with oil. Okay, but both of these methods actually are not infallible, because as the liquid condenses on it and then flows down, it just wears away the surface coating, and therefore it's not effective. So once the additives are worn away, or the liquid the oil film is worn away, then the liquid film starts wetting the surface, and the dropwise condensation gives way to film condensation, and therefore the overall heat transfer coefficient again comes down. Okay, so these are two methods which are possible but not very successful in terms of practical applications, as has been seen by experience. The third possibility is to coat it with things like Teflon or other polymer. So this coating is more stable because the polymers stick to the surface better. But the problem is, if the thickness of the coating is more than 20 micrometers, then because these polymers also have a poor conductivity, if the thickness of the film that is coated on the surface is exceeding 20 micrometers, the resistance that is offered by the coating more than offsets the gain that you get in heat transfer coefficient. So heat transfer coefficient might go up 10 times, but there is an additional resistance of the Teflon that is added. So liquid surface, there is the resistance of Teflon, and then there is resistance of H, okay, 1 by H. And what you find is that 1 by H might go down, sorry, H might go down by 1 by H might go down by a factor of 10 when H goes up by a factor of 10, but then this increases so that the total actually offsets the advantage that you got by increasing the value of H. So that is the problem with Teflon, and a stable coating of any of the polymers actually needs thicknesses comparable to this or more, and therefore this is also not a very effective method, but it's used in some places. The fourth option is to coat the surface with noble metals. Noble metals such as gold, platinum, or such materials. So then it is very effective, but then you can understand that it's very expensive. Imagine a gold plated heat exchanger surface. It's quite an expensive proposition, and therefore a difficult thing to practice. Okay, so but these practices are in vogue. People do use these in order to attain dropwise condensation wherever it is possible. Right? Mainly because this phenomenon is so complex, because number one, the nucleation depends on the nucleation sites, and the location of nucleation sites is an uncertain thing. We cannot predict where the nucleation sites would be, the surface defects or cracks or asperities of various kinds. It's difficult to predict where they would be. Secondly, once the nucleation happens, from the nucleation sites it flows downward, so it's a transient thing, and different droplets from different locations keep falling and rolling over, and therefore it's very difficult to analytically model this phenomenon because the phenomenon is complex. Okay, so no unified theory is derived. No unified theory exists. So you basically depend on practice or practical things. So what you normally do is to do a film condensation analysis, as was done in the earlier part of this lecture and the last lecture. You would have use a film condensation method and then say H dropwise is approximately equal to 10 times H film. So H bar dropwise is approximately 10 times the H bar film. So you would calculate the H bar film from the analysis that we have done in the earlier part of the lecture and just multiply it by 10 to get an approximate value of the H for the dropwise condensation. This is normally what is done for estimating the dropwise condensation heat transfer coefficients. Okay, so that's about condensation in a nutshell. We'll stop this lecture here. In the next lecture or next couple of lectures, we'll basically be talking about boiling heat transfer. So we'll understand the physics of pole boiling, and then understand what is nucleate boiling, what is transition boiling, what is film boiling, and understand the various regimes of the pool boiling, and also understand flow boiling. So this is basically what we will be doing it, and look at the heat transfer coefficients corresponding to each of these, much of which also depends on experimental observations and correlation of data. Okay. So that's what I have for this lecture. We'll stop here and we'll continue in the next lecture with boiling. Thank you.